Good morning to one and all present here. Myself Dr. T. Jagdish, working as Assistant Professor 3 in the Department of Electronics and Communication Engineering, KPR Institute of Engineering and Technology. So now we are going to discuss the topic on Laplace equation and the application of Laplace equation to determine the capacitance. So Laplace equation is derived from the Poisson equation, where the Poisson equation says del square V is equal to minus rho V by epsilon, where this rho V is the volume charge density rho V is the volume charge density. So this equation says del square V equal to minus rho V by epsilon. When the volume charge density becomes 0, then this Poisson equation becomes del square V equal to 0. So this del square V equal to 0 is called as Laplace equation. For any homogeneous and linear medium, we can say del square V is equal to 0. So this equation is called as Laplace equation. Now the main application of this Laplace equation we can use to determine the capacitance and inductance of any conducting material, of any conductors. So we can use this Laplace equation to determine the capacitance and inductance of a conducting material. So to find this, now we will use this Laplace equation and find the capacitance of a spherical capacitor. We will be using Laplace equation to find the capacitance of a spherical capacitor. So a spherical capacitor consists of two concentric conducting spheres, and let us take the radius of the inner conductor be A and radius of outer conductor be B, and the voltage at the inner radius is V0 and voltage at the outer radius is 0. So this is our assumption. We will see how we can use Laplace equation and estimate the capacitance of this conducting material, spherical capacitor. So we know Laplace equation says del square V equal to 0. Since it is a spherical coordinate system, as we have taken sphere, since it is a spherical coordinate system, so this del square V can be written as del square V is equal to 1 by r square dou by dou r of r square dou V by dou r is equal to 0. So as we know, this spherical capacitor is a function of only radius. As we could see from the diagram, it is function of only radius. Therefore, dou theta and dou phi components are 0. Dou theta and dou phi components are 0, since your spherical capacitor is function of only the radius, inner and outer radius. So there is no function of theta and phi component, hence d theta and d phi components are 0. Hence we have written del square V equal to 1 by r square dou by dou r of r square dou v by dou r equal to 0. Now let us take this as equation 1. Now this equation 1 can be written as it is equal to 0, dou by dou r of r square dou v by dou r equal to 0. We can write like this. So let us take this as equal. Now let us integrate equation 2. If I integrate equation 2, I will get r square dou v by dou r equal to, let us take capital A, where this capital A is your integrating constant. This capital A is integrating constant. So now let us take this as equation number 3. Again, and before integrating, I am going to simplify this equation, like I am going to rewrite this equation as, this can be written as dou v by dou r is equal to a by r square, or dou v equal to a by r square into dou r. Let us take this as equation 4. Now we will integrate equation 4. So if I integrate equation 4, I will get v is equal to minus a by r plus the integrating constant b. So minus a by r plus b. Let us take this as equation number 5. Now we will fix the boundary condition for this capacitance. So let us take the boundary condition. So the boundary condition, what we have assumed is, if the inner radius is a, my voltage is v0, and if my radius of my outer conductor is b, then the voltage is 0. This is our boundary condition. Now we will use this boundary condition to solve the equation. So if I substitute r equal to a and v equal to v0, so I will get v is equal to a by a plus b, that is v0. This is equation number 6. And 0 equal to minus a by b plus b. This is equation number 7. Now let us solve the simultaneous equation 6 and 7 to find the constants a and b, integrating constants a and b. So using this, let us find the integrating constant a and b. So if I solve, my answer will be, my b will be v0 into a by a minus b, and my a will be ab by a minus b. So this is my answer after finding the constants a and b. Now if I substitute the constants a and b in equation 5, I would get v is equal to minus v0 by r into ab by a minus b plus v0 into a by a minus b. So this is my v. Let us take this as equation number 7. Now we know that E is equal to, electric field E is equal to minus del B, gradient of V. So to find E vector, that is minus, see, you know, the function B does not depend on the radius, but it does not R, only the component integrating constant A depends on R. So my answer will be, after differentiation, you will get AB by A minus B. This is my E vector. Next, let us write the magnetic flux density, which is epsilon into E. So the answer will be minus V naught epsilon by R square into AB by A minus B. Let us take this as equation 8. Now we know that the surface charge density rho is equal to magnitude of D vector. So your magnitude of D vector will be V naught epsilon by R square into AB by A minus B. This is equation number 9. Then we'll calculate the charge Q. So Q is integration of the surface charge density over the given surface. So if I substitute Q will be integration of V naught epsilon by R square AB by A minus B into ds. My ds is the surface area of a sphere. Since it is a spherical capacitance, my ds will be surface area of the sphere. So my surface area of the sphere is 4 pi r square. So what happens? My r square and r square will get cancelled. So what is my q? My q will be q will be V naught epsilon AB by SB into 4 pi. Let us take equation number 10. Now we know the formula, the capacitance can be calculated by the formula Q by V. So we know Q, just substitute Q, and we know V. If I substitute Q and V, my answer will be C is equal to 4 pi epsilon naught into AB by A minus B. So this is my capacitance of a spherical capacitor. By using Laplace equation, we have derived the capacitance of a spherical capacitor. Thank you for watching.